So let's go ahead now and we'll see how we're going to implement the rounding in our multiplier. So if you go to the resources section, there's a Logisim file there and it's called fpm_NN_rounding. So if you go ahead and you open that up and we'll have a little talk through it. So once it's opened up, if you go to the top levels, that's the multiplier_NN_test, you'll be at this level here. And we've seen this in the previous videos, there's no change here. So let's drop down inside it. So this is ostensibly the same circuit we've seen in the previous video. But I've gone and I've added in the sticky bit, the rounding and the increment. And we're going to talk through these. Also, I've had to change the shifter section a little bit as well. So these sections here have been added. Another thing that's different as well is that the output here from the mux for the mantissa went straight out, but now it's going into this incrementer, and also the control here for this mux was coming straight from this 48th bit of the most significant bit of the multiplication, but now it's going through an OR gate and it can get incremented either through that 48th bit or through this incrementer. So I don't want to labour too much on the details of rounding. There is a rounding video on the first course in the design a floating point unit. So if you haven't already looked at that, I suggest you can go and have a look at that. But since we're doing rounding here, I might as well just have a quick verbal recap so we know what we're talking about here. If we were going to round, for example, decimal numbers, so we had the decimal number 5.4, then we would round that down to the value of 5. And if we had the value 5.6, we could round that up to the value of 6. But what happens when we've got exactly 5.5? Well, if we've got 5.5, what we could do is we could look at the other decimal places and we could see whether we've got any value in any of the other decimal places. So for example, if we had something like 5.506, then because we've got a value in one of the other decimal places, we're actually above the value of 5, so again we can round that up to the value of 6. But what's going to happen if, in order to do that, what you could do is you could logically OR all of the values. So if there's any one value in any of the decimal places after the 5.5, then we know we're a number bigger than 5.5. But what happens if you did a logical OR and it came out as a 0? That means that we've got exactly 5.50000 on off to infinity, so we've got exactly 5.5. Are we going to round up or are we going to round down? So what they do is they choose a round to even, and the idea behind this is that if we have exactly 5.5, what we do is we look at the number that we're trying to round to. So in this instance here, it's a simplified version because we've only got one number, so it's the value 5. So if we're going to try to round to the value of 5, well, 5 is an odd number. So what we would do in that instance, we would actually round that up to the value of 6 because we're rounding up to that even number. And the idea then is that if we had the number, say it was 6.5, 6.5 would round down to the value of 6. And if it was 7.5, it would round up to the value of 8. And if it was 8.5, it would round down to the value of 8. So the idea then is that we're always rounding to the even number. And the reason for doing this is we're going to cut out any, we're going to have half the time we're going to be rounding up and half the time, statistically speaking, we're going to be rounding down. So if you're rounding up and rounding down statistically half and half, then you're going to cut out any variations that you're going to get from continually rounding down all the time or continually rounding up all the time. So that's the idea of the round to even. Now again, if you want more details, you can have a look at the video and it goes through this in a bit more detail. What we want to be able to do is understand what we've got in the circuit here, so let's crack on with this and we'll see how we're implementing this rounding. So the first thing we want to do is we have a look in this shifter. Now you'll notice I've added this little section here, and what we're doing is we're taking in the least significant 24 bits, and we're doing roughly the same as we did here with the most significant 24 bits. So it's not easy to explain this here, so what we'll do is we'll go into the spreadsheet and we'll see exactly what we're doing with this and why we've added this little section. So go ahead and open up the spreadsheet, and if you head into floating point multiplier, now we're going to multiply together two kind of random numbers, so we'll just put in a few numbers here. Now that's just off the top of my head. Now what we're interested in is, in fact in this case here we've actually got a leading 0, so we could do it and we could end up with a leading 1. So I'll get rid of my image here so you can see that. So we've got a leading 0 here, but we could have put another number in and ended up with a leading 1. So let's just close this down, okay, because what we're interested in is what's happening in the spreadsheet here. So let me just zoom out a little bit, make this a little bit smaller. So we know that because this has got a leading 1 here, we don't need to normalise this. Okay, so it means that the mantissa we're going to pick off is going to be from this point, and we're going to count along the 23 bits. That's 23 bits. Now I've done this in yellow below, so this is the mantissa here. In this instance it goes from there to there. Now the next bit after the mantissa is going to be called the guard bit. So this isn't actually part of the 32-bit floating point number. If you like, this would be the 33rd bit. So that's the guard bit, and then the other 22 bits you see here, we're going to use this as to find out our sticky bit. So this is what we're going to use to do the logical OR on. So we'll be using this as the guard bit and this is the logical OR, and also the least significant bit of the mantissa is going to be that bit. So we're really interested in this bit here, this bit, and all of these bits. We're going to use the least significant bit of the mantissa. We're also going to use the most significant bit of the last 23 bits, and we're going to OR these 22 bits here. So these in effect become our sticky bit, our guard bit. But there's a problem in doing this, and that is that whenever we work through a different multiplication, if we ended up with, for example, a 1 in the topmost bit, that would mean that we would have to shift the decimal point up in order to normalise it. But in the process of shifting the decimal point up, it means that now the mantissa wouldn't start from this point and go down 23 bits. It's now going to start from this point here and go down 23 bits. So it means now that the guard bit is now going to be this bit, and the bits that we're going to logically OR to get our sticky bit aren't going to be these 22 bits, it's going to be these 22 bits. Now this tends to be left out a lot because it doesn't make a huge amount of difference. There's going to be, if you just didn't bother with this and you were just using the multiplier just for a bit of fun, then it would be fine. But obviously if you want to design something correct and that allow you to happily and safely take someone to the planet Mars, then you're going to have to take care of these things. So in this instance we'll just talk through it and we will actually take care of it because it's not too difficult. Now we've already seen in the previous video that in order to get the correct mantissa value, so the correct mantissa value, we were either going to go from this point and count our 23 bits, or we were going to go from this point and count our 23 bits. Now we've got a very similar problem here. In order to work out what bits we're going to use for the rounding, we're going to go from this point and go 23 bits. And we're going to go from this point and go 23 bits. So in effect it's the same type of problem, we're just shifting. But in this instance here, we're going to be shifting just in the opposite direction. So we're going to be, this one's shifted from here to here. In fact, no, it's actually shifting in the same direction, it goes from here to here. And this one's going to be shifting from the here to here. So we still got to use that same shifting mechanism that we used for the most significant bits here, and we're going to use that shifting mechanism for the least significant bits. Okay, so that's the reason for changing the circuit. So let's go ahead and we'll have a little look inside that circuit again. So you can see inside the circuit, what I've got is the 24 least significant bits of that multiplication. So that's the 24 bits of the multiplication. So that starts from this point here. Okay, so that point there gives us, from that point over to the end there, gives us our 24 bits. But we're going to be either starting actually from this point or this point, and we need to be able to start from either of them. So let's go ahead and we'll see how that is done here. So you can see here we've got those 24 bits, and we'll see where we got them from first of all. So if we come down here, we can see I've picked the 24 least significant bits for the multiplication, and it goes into the shifter, so that's a little extra bit I've added in. So whenever I head down inside, we've got those 24 bits. Now the 24 bits will either come straight through and we chop off the most significant bit, and we chop off the most significant bit, that's going to give us the 23 bits that we require whenever the 48 bit here is a value of 0. And if the 48th bit here, which is the 48th bit, that's me taking it here, so this is the most significant bit of this here, whenever this is a value of 1, we're going to have to shift the least, this here, to the right by that value of 1, and then we're going to have to cut off the most significant bit, and this is going to give us the proper output. So we're going to have, again, two different outputs from this little section. Now, awkward to describe in words, what I suggest you do is if you were to open this up and just put in a few numbers, and you'll be able to check and see the two different shifts. Now the choice of the output is made by the most significant bit here. So for example, if this most significant bit is a value of 1, then we're going to make the choice the bottom choice here. So it's going to come through this route here, and the output is going to be given here. Now if the most significant bit is a 0, then we don't come through this route here, we're going to come through straight through this route here, and we'll get the other output. So this is just going to give us our two different outputs that we've seen that we wanted in the Excel spreadsheet. So let's move on. So now we've got this extra output, so this will give us the correct 23 bits coming out and into this little sticky bit. So let's get into this sticky bit section. So you go up into that FPM underscore sticky, that's it there, and just double click on it. So you can see what we've got in here, as I mentioned, is just going to be our logical OR. So I'm going to have the 22 bits OR together. Now we don't OR together all 23 bits because the top bit here, or the 23rd bit, is actually the guard bit, so we don't do the logical OR with the guard bit, we just do the logical OR with the 22 remaining bits. Now obviously if you were going to actually implement this, you wouldn't be using a 22 input OR gate, but that doesn't matter. We just want to try and get something up and running in Logisim before we go on in a later course to actually look at how it would be implemented. So this is the sticky bit, and it's going to give us a value of 1 if any of these other 22 bits are high, but if all of the 22 bits are low, then it'll give us a value of 0, and in effect we would be sitting in that in-between spot, that tie, the 5.50000 off to infinity. So let's go ahead and we'll see what happens from there. We've got the sticky bit, and we've got that output from the sticky bit comes into the rounding section. So this is the bit we're going to talk about next. So you can see the rounding section's got 3 inputs and 1 output. So one input comes from the sticky bit, which we just looked at. The other input is the guard bit. So that's going to be the 23rd bit, which we just looked at a second ago in the sticky bit. So if we go back in there, just have a quick look, you can see it's going to be this 23rd bit. So we're going to take this one here, and we're going to use that as the guard bit. So we've got that guard bit there. Now we've also got the mantissa value, and of course the mantissa is going to have 2 possible values dependent on whether the 48th bit is a 1 or a 0, and that will have already been made, choice will have already been made for us here, and we're able to pull out that mantissa bit and put it straight into the rounding section. So let's go into the rounding section, we'll see what's in here. So all we really have here is a little bit of combinational logic, and that combinational logic does what we have here in this truth table. Now this truth table is explained in the first course whenever we talked about rounding, but I'll quickly go over it now. We're going to have 3 inputs. We're going to have this least significant bit of the mantissa, so that's the least significant bit here, and we've got access to it via the splitter. So in effect the least significant bit would be the 32nd bit of our single precision floating point number. Now the next one along is the guard bit. Now the guard bit would be this bit here. So if you like, the guard bit in effect would be the 33rd bit of our single precision floating point number. Now obviously we don't have a 33rd bit in the end, but we do have access to all of these other bits. And then finally we've got this rounding bit here. Now the rounding bit in effect is this sticky bit here, and the rounding bit are the remaining 22 bits which we see here, which have been ORed together. Now if all of them are 0, that means that the sticky bit is a value of 0, which really tells us that we're in a halfway position, but we'll see that in a minute. So that's a sticky bit here. So in effect this bit here is this column, this bit here is this column, and this bit here is the 3rd column here. So these are the 3 inputs, if you like, and we're obviously going to have 8 values for those inputs, and we're going to have all of the outputs here. Now let's just talk through the tied inputs first of all. Now if we have, for example, the guard bit as a value of 1, but the rounding bit here is a value of 0, so that is all of these sticky bits are values of 0. That means we're at a halfway point, so we're kind of like at 5.5. So in that case, what we do is we have a look back and we see, well, what is the value of this least significant bit? Is it even or odd? Now in this case here, when it's 0, it's an odd number. Sorry, it's an even number, and you can see that if you do a few conversions between binary and decimal, and you'll see that in order to get an even decimal number, the last binary digit will have to be a 0. So in that case we use the round to even. So we already know that this already is an even number, so we don't bother adding 1 onto it, we just round down to that even number. Now the other tie position that we're interested in is whenever the value is a 1 for the guard bit and the value is a 0, so we're exactly halfway, But in this instance here, we look back at the least significant bit of the mantissa, and we see that the least significant bit is in effect an odd number because it ends with a value of 1. So what we want to do is round this up to the nearest even. So if we add a value of 1 onto it, in this column we would have 1 plus 1, which would then give us a 0 in this column, and we would carry the 1. So that means we would, in this instance, have a 0 placed in this last digit. So this would mean that the answer we get again would be an even answer. So this means that what we're doing is we're rounding to even, but the last digit, statistically speaking, half the time will be even and half the time will be odd. So half the time we'll be rounding up and half the time we'll be rounding down. So it stops any statistical variations due to continually rounding up or continually rounding down. Now the other ones here, we quickly go through it. If the guard bit is a 0, so that's those 1, 2, 3, 4, then the output is always going to be a round down, it's always going to be 0. So that's us dealt with 6 of them. Now the 7 and 8 we're going to have here, if the guard bit is a 1 and the round bit is a 1, that means that we are going to be just above the above the threshold. So for example, it would be equivalent to being 5.51 or 5.52. Sorry, we would be just above the threshold, so it would be equivalent to say it would be 5.6 or 5.7, and we would be rounding up to a value of 6. So we put a 1 in here, so this would be a round up. And I think the last one we have to look at is this one here. Again, we've got a 1 in the guard bit, and we've got a 1 in the rounding bit, and it's already a value of 1, and we just again we round up again. Okay, so if you're not sure about these, you can always go back to the video on the first course on rounding, and it goes through it in a bit more detail than I have here. But that's ostensibly how it's going to work, and that's what we have here with our rounding section. So the final section here is the incrementer. Now the whole point about the sticky and the rounding and changing the shifter here, it was just to give us this one value coming out. So it's either going to be a 1 or a 0 coming out of the rounding section. So if it's a 1, it's telling us that we're going to have to round the value of the mantissa. So we're going to have to add 1 on to the least significant bit of the mantissa, and that 1 could be rippled all the way up through the mantissa. Not only can it ripple all the way up through the mantissa, it can also ripple out and onto the exponent as well. And this is what this line here is. This would be the increment rippling through not only the mantissa but also up into the exponent. So let's have a look and we'll see inside this incrementer. So again, this is quite straightforward. We've got the mantissa coming in. We're going to have the value that would potentially be incremented. So this is the value that's coming from the rounder. So again, I'll just have a quick look and I'll show you that there so you understand. So that's this value here. So it's just coming from the rounding. So we'll head back into the incrementer. So it means that this rounding value is going to be a value of 0 or 1. So we're just going to add that value of 0 or 1 onto the mantissa. Now we have to put it through this extender because this is only a single input, and it has to be a 23-bit input here. But it's still going to just be the value of 0 or 1. So we're either going to get the mantissa coming out as it was previously, or we're going to get the mantissa with a value of 1 added to it. But of course, if the 1 was to ripple all the way up through the mantissa, so for example, if the mantissa were all 1s here and we added a 1 onto the value of it, it means that that 1's going to ripple all the way up through, and we're going to get a carry out here. And this carry out is the value that you would now take to the exponent, which would add 1 on to the exponent. So in effect, this is the carry, this is the addition running all the way through the mantissa and then coming out and then adding on to the exponent bit as well. So finally, we would have the final output then for the mantissa coming out here, and we have a final output for the exponent with the potential of a carry here, or the potential of a shift in as well from the 48th bit of the mantissa, and we'll have the sign bit as well, and we'll have our final output. So that's everything we have on the rounding for the normal times normal, giving a sort of normal result for a multiplier. Now, there's quite a lot involved in this video. It didn't seem that much whenever I actually went and did the design, but actually explaining it in words is quite lengthy, takes a bit of time. Now if you get stuck with it, the best thing to do is to go into the shifter here. Well, in fact, the best thing to do is to go to the top level and put in a few values to multiply, and then compare these with the Excel spreadsheet. And if you can understand how this here models what's within the Excel spreadsheet, especially within this shifting section here, and the key to it is really just this little shifting section, this section here. And if you understand this, the rest of it is quite straightforward. So I think that's enough for this video. In the next video, we're going to then do something that's a bit easier, which is going to implement the special cases. So the special case is going to be not a number, the multiplication by 0 and plus and minus infinity. So thank you for listening. I'll get you in the next video. Goodbye.